Hey everyone, I'm recording this video under the Java hood, where we're going to talk a little bit more about understanding strings and the difference between strings and other data types. And, we've kind of been dancing around this idea of how strings are technically objects, but they're treated differently and they act like primitives and mutability. And just we've sort of been throwing around these words, and I want us to take some time to just really understand them. A lot of this is more of like a deep dive into strings and like how it works under the Java hood. Nothing here is going to be like hardcore tested or anything like that, but it will hopefully help you gain a deeper and better understanding of what Java is doing when it's running your code and when it's sort of operating. So the first thing I want to just touch on here is things that you already know or should know before going through this video. So you should know how and where objects are being stored and how and where primitives are being stored and like the differences between those two words. You should also know the difference between using equals equals and dot equals. Uh, when we're talking, I guess you can't really use dot equals on primitive data, but like just how you would use equals equals on primitive data, what the difference between equals equals and dot equals is for like arrays and user defined objects, as well as the difference between passing a primitive data object versus like an object reference into a method in Java. And we will talk a little bit about mutability, like mutable versus immutability, but you should sort of know those words when coming into watching this video. If those are words you don't know, if these are topics you don't feel comfortable in, then go check out my other videos in my introductory playlist, so that you can have a better understanding of sort of the basis of objects before you come into this video. Okay, so the first thing we have to talk about is where does your code actually run? And one of the nice things, one of the reasons why we love Java is because we have the Java virtual machine. It's abbreviated JVM. And we love Java, or I guess people love Java because it doesn't matter if you're running like a Windows machine or iOS or like a Unix, like a Linux machine, or like it doesn't matter what your operating system is, Java will work and it will work the same. And that's not true for all programming languages. And that's because of this JVM, because of this Java virtual machine. So what this means is when we oops, my screen on for me like rotated. I'm just going to like lock it so that that doesn't happen again. So what we need to understand is we write a .java file. This gets compiled into a class file, which is like bytecode that a computer can read. And then this class file is the file that's actually executed. We execute the class file. And this is important for us to understand because this is happening inside this virtual machine. And if you've never heard the term virtual machine before, what we're basically talking about is a special segment of memory that Java is going to allocate and use for like it's a little mini running machine that Java runs its own stuff in and its own environment in. Okay, so when we download Java, we download the Java runtime environment or the JRE. That comes in our Java development toolkit, the JDK. So hopefully you remember when we started, like first thing you did when you downloaded like Visual Studio and you had to download Java and get it running on your computer, you had to download the JDK, and the JDK actually came with the Java runtime environment and the Java virtual machine. So that was all part of this. Now, when your code is running, the Java virtual machine actually takes a big chunk of memory, and it's sort of broken down into a bunch of different pieces. So this virtual machine comes with lots of different things like class loaders and ways to compile things and read things, and there's all these different pieces to it. But the pieces we're going to focus in on have two different sort of types of memory. We have our runtime stack, our runtime stack memory. And we're also going to focus in on our heap memory. And our heap memory, as we're very quickly going to learn, is actually technically separated into subsections as well. We have one section over here, which we are going to learn is called the string pool. Whoops. And that's kind of where our This is the string pool. This is kind of where this video is heading, is for us to understand the string pool piece. So when we run our code, we've discussed this before that, we run our code and our runtime stack kind of helps keep track of really in abstract terms, what method call is we're working through and like our different variables. And we've mentioned before that we know that primitive data is stored on the runtime stack sort of directly int X, but object data like an int array A is going to be stored over here somewhere. And we've also mentioned that strings kind of act like primitives. And we've said that those are also going to be stored on the runtime stack. Now, that's not actually quite true, as we're going to learn in this deeper dive. But we have this separation of memory and where things are being stored and how things are being accessed. And basically, our runtime stack is either storing addresses to big chunks of memory from our objects, or it's storing the values directly for our primitive data types. Okay, so let's just make sure that we understand what is happening during compile time versus what's happening at runtime. So we have variables and declarations and initializations and literals, and we have to make sure we actually know what these words mean. And without going crazy deep into it, these do each mean different things. A variable is the name that we associate with that box for a given box of a given data type. So if we have a variable int A, this is the variable. And by saying int A, I could have put this somewhere else, but like this whole this whole line here is our declaration. Declaration. So what we're actually doing is we are declaring a variable A of type int. Okay, so those are two different words, variable, declaration. Now, an initialization is when or an assignment. Sometimes this will also be used, or the word instantiation. So when we're using one of these words, what we're talking about is like that equal sign, when we're actually assigning a value to our variable. So any of those words, if we're going to like initialize, would be like the first time you do it. So initialize is technically like the first assignment, but it is just a type of assignment of a variable. And so we do initialize or assignment, initialize the first assignment of a variable. Instantiation often is referring to like the memory allocation with objects, but they sometimes get used interchangeably. Or we can just say assignment is when we assign a value to a variable. And I'm being very careful here in using the term value because assignments can look different. For example, pretend we have a scanner, int A equals scanner dot next int. This is absolutely assigning a value, right? That's an assignment. But if we say int A2 is equal to 5, this is also an assignment. But there's a big difference between these two lines of code right here. There's a huge difference, actually. They both are assigning a value. However, let's just highlight these in different colors. This one here is assigning a value, and it's going to have to happen at runtime, right? It happens at runtime because we don't have all the information at compile time to give that value, to give that variable a value, right? Because we have to ask the user. We're scanning something and getting it from the user. That's going to happen at runtime. So this is the assigning of a value, but it has to happen at runtime. Now, if we look at this one down here instead, this one is indeed an assignment of a value. However, more specifically, it is the assignment of a literal, right? It is a literal value. It is the value 5. It is something that we already can see and know and touch, and we can do it at compile time. And there is a big difference between if it happens at runtime and if it happens at compile time. And the big difference we're going to really see is going to be when we talk about strings. But here we are understanding the difference between each of these words. So recap, a variable. Our variable is like our named variable, our named portion of our declaration of how we're going to refer to a specific pocket of memory that's holding a value. Next, we have our declaration. Our declaration is that entire line where we both announce the variable, its name, as well as its data type. Third is our assignment or our initialization. And this is when we're actually assigning a value to our variable. We're actually assigning the value. And finally is this word literal. And the literal is when we have an actual hard-coded value of some kind that is going to be assigned to a variable. Now, a literal does not have to be a constant, right? We'll notice that this isn't a constant. It's just got an initial value of 5. Just like it's possible for us to give a string, let me just put it right over here, result, an initial value of hello. And perhaps we will concatenate onto that later. Perhaps we'll reassign it. But a literal does not have to be a constant. Most of our constants, most of our final variables are literals, but we also know that it doesn't have to be. Those two words are separate from each other. A literal variable assignment does not need to be final. And a final variable, I guess now it's a constant, so a final constant value, right, may not come from a literal assignment. They are not the same thing and they don't have to be connected. So that's important to understand that they're two different things. There's no rule that connects those two words together. Okay, so let's talk about this compile time step and what that has to do with the Java virtual machine and what that has to do with strings. So we did talk about how we have these two different heap segments. Let's take another look at that. Now, we have our heap, as I often draw as my magical cloud. And anytime we use the new keyword, whether it's at compile time or at runtime, when we use that new keyword, we're making some data. We're allocating some memory on our heap, and we're storing some data on our heap. And then our runtime stack, which I'll abbreviate RTS, gets a reference to that memory space, right? So this is our object. That's the variable object that we're going to name it, whatever it's going to be. We have our data type, and then we can go ahead and allocate it over here. Now, that's what a lot of the heap memory is allocated for. However, Java knows that we use strings for a lot of different things. And so what does Java actually do? Ta-da! String pool. It takes a memory segment over here, somewhere in the heap memory, and it allocates some of it to what we are calling the string pool. All right, so let's learn about the string pool, which is the string pool is going to be, I'll abbreviate it SP, is a segment of memory found in the heap. So it's not on the runtime stack, but it's found in the heap, which is, don't forget, in the JVM, in the Java virtual machine, which is dedicated to, and I hope you guessed it, strings. And Java does this because we use strings so frequently that it really hopes that it can kind of reuse some strings. So we have a pool of strings, which is exactly what it sounds like. So anytime that in your code, you go and write some code like string s equals hello, string s2 equals hello, string S3 equals world. Let's just define these really quickly. These are our data types. These are the variables. This is the assignment of 3 string literals. Because these are string literals, meaning that this assignment is very obvious, we can see right at compile time. Java at compile time will take those 3 words and shove them into the swimming pool of strings. So we have hello and we have world. So at compile time, this is like, I feel like I need to write that somewhere. At compile time, Java first creates this string s equals hello. It puts hello into the string pool and it's got s right here. Fantastic. Then it goes to S2 and sees that it's also hello. Before it allocates new memory for the second hello, it actually goes to look in the string pool, sees that hello is already there, and gives it the same hello value. So these are basically the same object right now. We have no easy way to tell that in Java, but they are. They're both the same object because the string pool already contained the word hello. Then the string S3 world gets created. World was not in the string pool, so it went and it plopped it into the string pool as well. So this is a segment of heap memory that is storing these string literals. This happens at compile time. Things that happen at runtime are different. So for example, if we have s equals hello, we're getting really deep here. This declaration with this literal is going to happen at compile time, but something like this, S2 is going to be equal to S plus an empty string. This is arithmetic. Now it's arithmetic on strings, but it's arithmetic. And that is not going to happen at compile time. That is going to happen at runtime. And this is the important differentiation, because when we do something like this, even though the resulting string, because this is an empty string, so even though the resulting string still says hello, this is not going to be stored in the string pool. This is going to be stored somewhere else in our heap memory with the word hello. So let that sink in for a second. There is a difference here. When we first just had a string literal, hello, that was stored in our string pool at compile time. But when we did our concatenation of the word hello plus some other string, and in this case, it happens to result in the exact same value, it will be stored in a different place. It will not be used here. This happens at runtime, and it's going to be stored over here. So let's take this understanding and let's look at what this means about equals, dot, and dot equals when it comes to strings. Let's take this exact same example. Let's do string s equals hello. Let's do string s2 equals hello. And let's do string s3 is going to equal s plus that string literal like that with the arithmetic. So the difference here is, again, this s is being assigned the literal hello. This s2 variable is being assigned the literal hello. This s3 variable is being assigned whatever is in s plus this value here as well. This is not a literal. A literal is not going to have math in it. It's not going to have arithmetic. This is not a literal. So when this program runs, we understand that our heap memory, which has never been drawn like this before, but now I'm going to, has 2 different sides. This is the heap memory. We have the object allocation over here, and we have our string pool over here. So when the code runs, we end up with hello in the string pool only once. This line runs, it creates hello. Then this line runs and it uses the same hello. So basically this points here, and this points here. And then S3 gets created, and it's going to make a brand new one right over here. Hello. It's going to take this one, S, realize that there's hello in there. It's going to add on this string literal, which does exist in here somewhere. We can pretend like that's right here because it's a string literal. It can be stored as a reference right here. It's not anything. And it's going to add these two values together and create a brand new string over here. And when you hear me say the word brand new string, you know it's going to be object allocation. It's creating a new string. We may not use the keyword new right here, but that is implied. And so it gets created right over here. So when we say S is equal S2, whoops, we can see that again, this equals, which we know does reference comparison. When we follow those arrows, actually is indeed still comparing the same thing in the string pool, right? We can see that that's the case. When we say S dot equals S2, now what's happening is this method is actually going to go and take the value at this reference in the string pool, hello, the value at this reference in the string pool, hello, and compare the contents of those two words, and they are the same. So both of these will indeed be true. However, now if we say S, equals S3 or S dot equals S3, we're going to get different results because now S, follow that pointer, takes us here, equals S3, follow that pointer, takes us here. That is going to be false. Those are not the same. They are not pointing to the same place. And our equals does a reference equality check, right? Not a contents equality check. It does a reference equality check. Dot equals is different. So now when we run this line, S dot equals, we're going to actually go into this, grab the contents and compare it to the contents of S3, grab the contents, and we see S3 and S, those two have the same contents. So this will return true. So we can now see that even though when these print, all three of these variables contain the same word, we have some very different behavior going on underneath the Java hood. We can see the difference between the literals and the arithmetic, where they're being stored, and how that memory address affects how we do these equality checks. Now, the last thing I'm going to say about this is, does this mean that the string pool is a compile time thing? Is there any way for us to somehow get this S3 onto the pool? Now, this is like purely extra information. You don't need to know this. This is just for interest's sake. And the answer to this question that I just asked, so the string pool is a compile time thing? No, it's not a compile time thing. Java actually gives us a way to move values from here over to here. So let's just drop this example one more time so that we can actually see what I am talking about. String S is equal to hello. We'll just do it with two values. String S2 is equal to S plus a blank space. System.out.println. Let's do S equals S2, which as we know will be false. Leave a blank line here for a second where I'm going to put some nifty code to understand this. And then we'll do one more print line where S equals S2. We're going to somehow get it to say true. Okay, what is this line here, right? That's the key. So here's our heap memory. And we're going to break it up into those two different segments that technically exist. We have our string pool. We have the rest of our heap memory. And let's go ahead and figure out what the heck is going on. So when string S is first created, this first line, we now understand that we basically get a reference from here boop, onto the string pool. Hello. We also understand that that happens at compile time. Then we have S2 is going to equal S plus this empty string. when at compile time, this empty string actually does get created over here technically. So we can even do that. We want to be really technical. And then we can say that S2 right here is going to get created as a concatenation of these two things together at runtime. So this was also compile, but this line here is runtime. And we get hello over here. And then we know at runtime, we do this equality check and we get false. Now, how the heck are we going to actually do that equality check and get true? Well, Java allows for us to do something like the following. S2 intern, which I think stands for internalize, but I don't actually know and I don't actually care because we're never using this. But we're, for interest's sake, we're learning it right now. This line of code right here allows us to say, please take that S2 value and move it over here, internalize it. So what happens at runtime when we run that line of code is at runtime, this gets freed. We free this memory. We go over to the string pool and we say, if this exists on the string pool, use that. Otherwise, make a new one. It already exists on the string pool. So this does this. And now when we run this line of code, oh my goodness, S goes over to this piece of memory, and then S2 goes to this piece of memory. And now our equality check does indeed give us what we want. We're not going to need to do this. There's no reason for us to do this. You should never actually need to do this right now. But it's interesting to see the difference and understand why exactly we're getting this difference in value when it comes to strings and the different ways in which we can manipulate them and the different reasons why we should never rely on equals equals because none of us are writing this line of code. So we don't use equals equals with strings. We use s dot equals. S2. And this only pertains to our string values for us right now because primitive values are never stored in heap memory. Primitives are always stored on our runtime stack. And any other object that we create doesn't have a special little string pool or array pool or anything like that. It's a non-issue for all other object types because they're all always going to be created over here. This is a unique to string situation that have access to the string pool that literals get stored in and get pulled from whenever we can. Okay, so hopefully that made some sense. Hopefully we have a little bit of a deeper understanding of how strings work under the Java hood. And as we continue to progress through this material, there may be more difficult concept videos that I will hopefully be able to break down for y'all. Thanks for joining me and have a great rest of your day. Bye.